Hello everyone, welcome you all to the next session on real numbers of class 10 mathematics. In this session, let's solve the remaining problems from exercise 1.1. Here is the second problem for us. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. We are supposed to prove if any positive integer is there, it takes the form 6q plus 1, 6q plus 3 or 6q plus 5. Now, let us assume any positive integer and let us take a, b any positive integer and we'll take another positive integer b. We'll choose the value of b as 6. The question says we have to prove it is in the form of 6q. So the number 6 gives us a clue that b should be chosen to be 6. Now when I have two positive integers say a and b, by Euclid's division lemma I will be able to write one in terms of the other. Now as per Euclid's division lemma, we will be able to write a as a equal to 6q plus r. That is your a is a dividend, 6 is the divisor, q is the quotient whereas r is the remainder. So if at all we have any two positive integers, we will be able to write the bigger number in terms of the other number, that is the divisor, quotient and then the remainder. Of course, the quotient should also be positive integer. Now the remainder lies between 0 to 6 because 6 is our divisor. When we see r lies between 0 to 6, it means that r can take the values from 0 to 5. That means 0, 1, 2, 3, 4 and 5. So we have a positive integer in the form a equal to 6q plus r where r takes different values from 0 to 5. Let's check what happens when this r is 0 or 1 or 2 and so on. And we'll try to identify whether the positive integer is taking this given required form or not. For which let me start with r equal to 0. When r equal to 0, a becomes a 6q. That is your r takes the value 0. So a equal to 6q is what you're getting for the value of a. When it is 6q, I'll be able to write it as 2 times of 3q. That is a can be written as 2 into 3q. If any number is able to be expressed in terms of 2 into something, then it is easily understood that it is an even integer. So this tells us that a is an even integer here. Now let me go for the second reminder, that is r equal to 1. When r takes the value 1, a becomes 6q plus 1. You can check it out. R is here. Value of r is changing here. When r is 1, a becomes 6q plus 1. Now here I won't be able to do anything with this one, but still I can express 6q as 2 into 3q. So you can see your a equal to 2 times of some number plus 1. So this is not actually an even integer because if at all we represent any number as a product with the 2, it is going to be an even integer. We have represented 6q as a product of 3q and 2, but still there is a 1 which is added to this product. So this tells me that this is an odd integer. That is a becomes odd in this case. That is when your remainder is 1, your a is an odd integer. Let's check for the remaining reminders here. When r equal to 2, we get a is 6q plus 2. Again, I have 6 and 2. When I factor out 2 from this, I can have it as 2 times of 3q plus 1. There is nothing added to this 2. This tells me that this a is an even integer. When r is equal to 3, you can check out the steps. We got it like it is an odd integer, and when r is 4, we get it as an even integer, and you can check when r is 5, your a is an odd integer. So we see that when r is your 0, you get as an even integer. So let us look for the places wherever we have odd integer. We can see when r equal to 1, we have an odd integer. When r equal to 3, again we get an odd integer, and when r equal to 5, we get an odd integer. So these are the places where we get a as an odd integer. Now when we have odd integer, what is the form that a takes here? When r equal to 1, our a takes the form 6q plus 1. Now let's see what is the next case here. When r equal to 3, our a takes 6q plus 3. Previous one we get it as a equal to 6q plus 1. Here a equal to 6q plus 3. And when r equal to 5, we have a equal to 6q plus 5. So when I consolidate everything, I could see r takes the form 6q plus 1 or 6q plus 3 or 6q plus 5. So these are the places where we get a as a odd integer and the remaining cases are even integer. So if at all I say a is an odd integer, it means it can be expressed in the form either 6q plus 1 or 6q plus 3 or 6q plus 5. Hence, we can conclude that every positive odd integer can be expressed in the form 6q plus 1 or 6q plus 3 or 6q plus 5. So, this is what we are asked to prove and we have proved it. I hope you can understand the steps here, and we are using a Euclid's division lemma which we had discussed in our previous session. Just go back to the previous session and recollect what we have done. Only then you will be able to have a better understanding for this problem. Now with this idea, we'll solve one more problem from the same exercise, and here is a fifth problem. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. We are supposed to prove here cube of any positive integer is of the form. So here we have 9m and again 9m, again one more 9m plus 1 and 9m plus 8. So this gives us a clue that our b can be 9, but I am choosing my b as 3 here. The reason is we are not just finding any positive integer like as we did for the previous problem, like any positive integer or even integer or whatever it is. Here we are supposed to prove that cube of any positive integer. So we are not just going to find out the value of a, that is we are not going to find out the expression for a, but we are going to find out the expression for a cube. Hence, it is enough if I choose my b as 3, because when I cube this 3, obviously I will be able to write the a cube in terms of 3 cube. So let me work out the problem so that you'll be able to understand why am I choosing b as 3 rather than choosing 9. Now, is it wrong if I choose b as 9? No, not at all. We can still choose b as 9 also. The only thing that will vary here is if you are going to choose your b as 9, you will have reminders from 0 to 8. That you can check it out here. See, in this I'm using b as 3 here. I'm choosing a as any positive integer and b as 3 here. So when I have two positive integers like a and b, as per Euclid's division lemma, I'll be able to write a as 3q plus r, where r takes a value 0, 1 and 2. So I will be discussing all the cases for all the reminders. It is when r takes a value 0, what happens to a cube when r is 0, what happens to a cube when r is 1, and what happens to a cube when r is 2. So with this I'll be able to come to a conclusion. But if you're going to choose your b as 3 instead of 3, if you're going to choose b as 9, you have to check for all the reminders from 0 to 8. To have a conclusion, it's not necessary that if you solve for 1 or 2 reminders, you have to check out the conditions for all the reminders from 0 to 8, that is all 9 reminders. To make the steps simple, and also since we are going to use cube of some number, it will be much comfortable to choose b as 3 for your calculations. Let's proceed in finding the solution for this one. As we have to choose, we have chosen a as a positive integer and b as 3. By Euclid's division lemma, we have a equal to 3q plus r, where your remainder varies from 0, 1 and 2. Now as we know, we are supposed to find out cube of any positive integer. So this tells us that we have to find the value of a cube, not just with a. So let me take the cube of a. So when I cube a, it must be cubed on the other side of the equation also. That means I will have a cube as 3q plus r the whole cube. Now this takes a form a plus b whole cube. I hope you'll know what is a plus b whole cube. Let me write it here for your convenience, or I'll write it from the next step. That will be okay. Let us check it out for first reminder. That is when r equal to 0. What happens to this a cube when r is 0? So when r is 0, we will have it like a cube is equal to 3 cube plus 0 because r takes the value 0 here. So 3 cube plus 0 is nothing but 3 cube the whole cube. 3 cube whole cube is 27 cube. Now I need to express the number in form of something with a multiple of 9. Now this tells me that if I factor out 9 from this, I will have it as like 3 into q cube. That is 9 into 3 q cube will be giving me the 27 q cube. That is 3 into q cube into 9. This 9 into 3 gives me 27. So I can factor out 9 from the entire expression. So that gives me 9 into 3 q cube. Now I need to express the expression in the form of some 9m. I don't need to have such a big terms like 3q cube and so on. So I'm going to replace the entire thing with some variable called m, where m takes the value 3q cube for this remainder. So a cube is equal to 9m. So I am able to express one of the cube of positive integers in the form 9m. Now I should not stop with this because I got one answer. I need to check for the other two reminders also. Here it is. When r is 1, our a cube becomes 3 cube plus 1 the whole cube. Now here is the one where we need to apply the formula for a plus b whole cube. I hope you remember what it is. Anyhow, let me write it once again for your understanding. So a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. I know I can even write it in the other form, but this will be much comfortable for me to simplify the expressions here. So 3q plus 1 whole cube, that becomes 3q whole cube, that is your first term a cube, plus 3 into a square. A square is nothing but your 3q whole square into b. B is your 1. Plus 3 into a into b square. So 3q into 1 square plus 1. I hope you are able to understand how I am doing the substitutions here. So that gives me 27q cube plus 27q square plus 9q plus 1. So 27q cube plus 27q square plus 9q plus 1. You can see the first three terms have 9 in common, but the last one, 1 doesn't have any factor as 9 here. So let me combine the first three terms. There is 27q cube plus 27q square plus 9q. Factor out 9 from each of this. That gives me 9 into 3q cube plus 3q square plus q whole thing plus 1. So this means that the entire expression, that is 3q cube plus 3q square plus q, can be replaced by another variable called m. So I can rewrite this a cube as 9m plus 1, where m takes the value of 3q cube plus 3q square plus q when your remainder is 1. I can understand like you have m for a different value for m in the previous remainder, and you have a different value for m in this remainder. Of course, the value differs based on your remainder, because when your remainder is different, your number is also going to be different. It need not be same. So with this understanding, we can choose the same variable here. Let's do the same process for a last remainder, that is r equal to 2. A cube is equal to 3q plus 2 whole cube, and you can see the expansions that are done here. It leads to 27q cube plus 54q square plus 36q plus 8, out of which again the last term, there is a constant term, doesn't have any common factor for all the three. So this is independent of 9 here. So I'm just combining all the first three terms and factoring out 9 from this, which gives me 9 into 3q cube plus 6q square plus 4q plus 8. Again, that can be written as 9m plus 8, where m takes the value 3q cube plus 6q square plus 4q. So thus I'm able to write a cube as 9m plus 8. Now you can see when your remainder is 0, a cube takes the value 9m. When remainder is 1, we have a cube is equal to 9m plus 1. And when the remainder is 2, we have a cube is equal to 9m plus 8. Thus, we see that cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. In this exercise, we have solved a few problems and we have proved a few problems based on Euclid's division lemma. There is one more problem left out for you in this exercise, and that is going to be your homework. So homework for the day is not only exercise problem, the question number 4 from the same exercise, and I want you all to try the examples. There are examples 1, 2, 3 and 4. So there are 5 problems for you to complete as homework after this session, and also keep practicing the other problems so that it won't be that difficult for you when we have next sessions. So with this, I wind up this session. We'll meet in the next session with the next exercise or next theorem. Thank you.